Okay, so hopefully you all enjoyed the 3-day holiday. So what we've got today is we're going to wrap up the equations that we've talked about, introduce the last big equation, and then show you how that all fits together, and then you can do some of your first real physics assignment. So, again, if you want to plan ahead, here's how the week is going to play out. So today is the first applications of these equations. Tomorrow is the same equations, just with gravity. Then we'll review on Thursday, test on Friday. Okay? Now, Friday is an early release day, but if you don't want to feel rushed, if you can stay after school and keep working on the test, okay? But if that's something that will impact your work, your ride, someone else, just be aware, and you can get it done in the time allotted, but you've got to work fast to get it done. But so if you want kind of a laid-back testing environment where you're not feeling rushed, just be aware of that test coming up on Friday, all right? So one kid, he literally, like every test, he would stay until like 5. So, yeah. Actually, we nicknamed him Pop. It was Pop. Yeah. Okay. Oh, he did. Yeah, he got very good grades, but he would just overanalyze things. So, okay. So here's where we're at with equations. So V equals V naught plus AT. Not explicitly written on your equation sheet is this 1/2 V plus V naught time. All that is just saying, oh, here's the average velocity, okay? Then out of that we came up with x equals 1/2 AT squared plus V naught time, okay? So this middle one is not technically on your equation sheet. Now keep in mind, here's what's going to happen on the test on Friday. I'm going to give you the test, you're going to get a laminated version of this and your calculator, and that's it, okay? So if you want to remember, oh, V plus V naught over 2 equals time, which is just the area of a triangle, if you want to write that down as soon as you get the test, great. But that's an equation, it's simple, it's just the average of 2 velocities. If you want to memorize it, sure it isn't much to memorize, it's just 1 plus 1 divided by 2. Okay, so let's look at a situation. So you're going to have the world famous carrot car with an initial velocity of 0 meters per second. So here's how this would play out. I would say a car is at rest, because these are all word problems, and is accelerated at 4 meters per second squared. Find the velocity and displacement at the end of 1 second, 2 seconds, 2 seconds, and 3 seconds, and then draw a position time graph, a velocity time graph, and an acceleration time graph. Okay? So, let's start out, oddly enough, let's start with the position time graph. Now, a problem like this, unless I explicitly tell you something different, you can just assume that where the car starts is the reference point, okay? The only time that really wouldn't be true is if you're dealing typically with like gravity problems, where the squirrel is on top of the cliff and the squirrel jumps up and then falls all the way off the cliff, okay? But unless you're explicitly told something weird like that, you don't have to worry about like that initial position. You just set your initial position equal to 0. Do not make it complicated. So, on your position time graph, assuming that you might have forgotten everything that I've taught you over the 3-day weekend, You have three options on your position time graph. Upper lip, middle lip, lower lip. What do you got?
Lower.
Lower, why?
It's exponential growth.
Okay, so it is, but how does it make it the lower
Because
lip?
the slope of the velocity graph is positive, and because acceleration is positive.
What?
Which is right. What does this, go to this, you jump to steps 4 and 5. What does the slope of a position time graph give you? Okay, so what does the upper lip show? Slowing down. What does the middle lip show? Constant velocity. Bottom lip shows it, because what's happening to the slope of the line?
Getting steeper.
It's getting steeper and steeper and steeper because the object is going faster and faster and faster. Okay. So we just got, I don't know what the numbers are yet, but we'll fill them in later. So as a general shape, I know by the position time the graph is going to go something like this. Okay? Now, what about my velocity time graph? Michael, what's my velocity time graph going to do?
It's just going to increase at a constant rate.
Boring? Okay. What's the slope of that line going to be?
Acceleration.
Which is 4 meters per second squared. Okay? Now, remember, this is going to be more important than we do with the forces. So F equals ma. What's the only way that you can change the acceleration? Change the force. So unless you're explicitly told that something is changing in the problem, use same, even though we haven't talked about forces, but here's the assumption, is that you have the same force acting over the same period of time, creating the same uniform acceleration. Okay? So unless you're explicitly told something different, the only way you can change the slope of a velocity time graph is to change the force, because that changes the acceleration. So unless you're told anything different, you assume that it has uniform acceleration. Okay, cool. Now, if you look at the information that you have, and some people like to do that, the V naught tax chart, okay? Some people like this. You don't have to do this, but if you read a problem and you're going, I got nothing, okay? Set up the chart, figure out what information that you have. Now, in this situation, you're told that the car starts at rest. So a lot of times either the final velocity or the initial velocity of the car is going to be 0. So in this situation, what's going to be 0? V or V naught? V naught, because you're told the car starts at rest. Okay? My final velocity is one of the things I don't know. I know my time could be 1, 2, or 3. I know my acceleration is 4 meters per second squared. Distance, also going to be a wild card. Okay? So let's deal with the velocity first at the end of 1 second, 2 seconds, and 3 seconds. There's a simple way to figure out how fast it's going at the end of 1 second. What's the easiest way to do that? Let's use the slope. What's your slope? 4. So at the end of 1 second, and if you start at 0, how fast are you going? 4 meters per second. At the end of 2 seconds, you're going 8. At the end of 3, you're going 12. That's what it means. Remember, listen to me, listen to me, listen to me. Acceleration is not how fast you go. Acceleration is the rate at which your velocity changes. So it says for every second that goes by, my velocity goes up by 4. That's all it means, okay? And if you start at 0, you're going to go to 4. Then you're going to go to 8. Then you're going to go to 12. If you started at 100, you would go to 100, 104, 108, 112, okay? Where you start doesn't matter. this is the same slope. Okay? Cool. Now, if you go, oh, but Mr. Burkham, oh, let's talk equations. We have these equation sheets. It's wonderful. This is physics, these equations. Wow. Okay, cool. So you could use V equals V naught plus AT. Right? What are you searching for? Which of those variables are you searching for?
Velocity,
Which one?
the one at the time.
Yeah, the final velocity. So remember, don't look at this and go, oh, physics is hard. It's the slope-intercept form. What does acceleration represent?
Slope.
Slope. X is your time. V is your final velocity. V naught is your y-intercept. Okay? Don't look at this and go, this is different from the math. It's applied math. Okay? Trust me, I taught math. It's boring. That's why I teach math, but I call it physics. Doesn't mean I can throw squirrels in the air that I couldn't do if I teach math. It's like if I throw squirrels in the air teaching math, people are going to question if I do it in physics. Oh, it's okay. It's just Burkham throwing a squirrel. Okay, so here's what we got. My initial velocity is going to be 0. I don't have to worry about that part of it. Basically, what we're saying is the y-intercept is 0. So then it's just a matter of taking, 4 meters per second squared times 1 second. I get 4 meters per second. And then I'd go 2 seconds, and I'd get 8, and then I'd go 3, and I'd get 12. Okay? Cool. Got it? Great. That's the equation side of it. Nice. Okay. Now, one thing I want to point out, and this will be huge in terms of how you view physics equations going forward. This had to be a linear function because it's just acceleration times time. There's nothing squared, there's no cubed roots, there's nothing weird about this, okay? This is as simple a relationship as you can get. So what this means is that velocity changes as a linear function of time. Not distance, not Oreos, nothing. Not force, linear. So because it's acceleration times time, velocity is a linear function of change with time. And you know that. If you don't believe me, just look at it and go, oh, that's just acceleration times time. It's just slope times an x value. That's all it is. Okay? Don't flip up. Now, let's talk about how far we're going to go at 1 second, 2 seconds, and 3. Could I do this? Could I say, well, at the end of 1 second, I was going 4 meters per second. I can take 1 second times 4 meters per second and go, oh, I went 4 meters. Cool? Wyatt, you okay with that?
I don't know.
It's yes or yeah.
No.
You say that with no confidence. Quit whistling. Hate whistling. Okay, Wyatt. What's the only time you can use distance equals velocity times time?
Velocity is constant.
Is this a constant velocity? No. What's the only time it's going 4 meters per second? At 1 second. It was at some point going pi meters per second. At some point it was going 3.8 meters per second. At some point it was going 0.2 meters per second. Okay? Velocity was continuously changing. Only at the end of 4 seconds, only at the end of 1 second are you going 4 meters per second. Okay? Only at the end of 1 second are you going 4 meters per second. Okay, that's it. No other time. No other time. None. I repeat, none. So this is why on this unit, unless I explicitly tell you that it's moving at a constant velocity, unless I explicitly tell you that, you have to assume that you're accelerating, which means if you find the urge to use that, stop. Don't. In accelerated motion, you cannot use distance equals velocity times time. Now, let's just jump back up here. We said at the end of 1 second, we were going 4 meters per second. Could I use my velocity time graph to find the displacement? What does the slope of a velocity time graph give you? Acceleration. What does the area give you? Displacement. Do you know that this looks like a little triangle?
Yes.
Yes. Ooh, how do you find the area of a triangle?
1/2 base.
Oh, can you do that? Oh, you can do that. So if you go, Mr. Burkamp, I just love finding areas of triangles. Cool. 1/2 base times height. 1/2 times 1 second times the height of 4 meters per second, and you're going to get 2 meters. Okay? That you can do. I don't recommend that. I do not recommend doing it that way. And here's the reason why. The reason I don't recommend that is because of the fact that you found that 4 meters per second. I did not give you that 4 meters per second as part of the problem. So if you screwed up that calculation of 4 meters per second, your next answer is going to be wrong, okay? So when you're working these complex problems, you want to go off of values that are given to you as long as you can. Now, you are going to reach points where you don't have a choice. You have to use previously found values. Some of these more, especially in the more complex problems, like you have to take the leap of faith and go, hey, I got to assume that this answer is right, okay? Now, but math to the rescue. What I would recommend is that you go, oh, x equals 1/2 at squared plus v naught time. Oh, what's my initial velocity? 0. Okay, don't have to worry about that part of it, okay? I know my acceleration, 1/2 4 meters per second squared times 1 second squared. Oh, check my math, I get 2 meters. Cool. I get the same answer, okay, which I should. I can't have one calculation getting me 2 meters and another calculation getting me 3.5 meters. It's like, well, which one's right? I don't know. Let's take the average. No, okay? Both sets of calculations have to produce the same units and have to produce the same numeric value. Now, here's what's important about this. When we did v equals v naught plus at, okay, when we did that one, notice that that was acceleration times time, and that produced a linear graph. This is at squared, which means it's going to produce a nonlinear graph because we're multiplying by t squared. Okay, so now we can do the same thing. The only thing that's going to change is that we're going to put in 2 seconds squared, and then we're going to put in 3 seconds squared. So you put in 2 times 2 squared is 4, 4 times 4 is 16, you take half of that, you get 8 meters, and you get 3 squared, which is 9, and then you get 18 meters, okay? So notice this is a non-linear change in position, because I go from 0 to 2, and then I go to 2 to 8, and then I go from 8 to 18, okay? This is what makes this a quadratic function. Now, here's where this all is going to come together. Okay? So stay with me here. Big moment. Big moment. So I'm going to try and draw this position time graph to like some semblance of a scale. Okay? So there's 1 second, 2 seconds, 3 seconds. And there's 4, 8, 12, 16, 20. Okay? Went up increments of 4. So 1 second I was at 2 meters. 3 seconds I was at, or 2 seconds I was at 8 meters. 3 meters I was way up here at 18. Okay? So I got this one. Now, this is hopefully where this all fits together. Here's my position time graph. It's a quadratic function, it's a curved line, it's getting steeper. If I went in here to the 1 second mark and drew a tangent line, what would the slope of that tangent line be? 4. Why? Yeah. What does the slope of a position time graph give you? Velocity. And because it's a curved line, we have to draw tangent lines because we're accelerating. So that line at exactly 1 second would have a slope of 4 meters per second, because that's how fast we're going at 1 second. Okay? Makes sense. Why? What would be the slope at the 2 second mark? 8. At 3 seconds, it would have a slope of 12. Okay? Steeper and steeper and steeper. If I were to find the area underneath that position time graph, what would that represent?
Why 12?
Because at 3 seconds, it's going 12 meters per second.
I thought it was going 18.
No, it was at 18 meters,
Oh.
but it was going 12 meters per second.
Oh,
Okay? If I were to find that area, what would that represent? It's a trick question.
Is it displacement?
Nothing.
Nothing. Why? What units would you have?
Meter second is.
You would have meter seconds. What's measured in meter seconds? Absolutely nothing. Okay? Nothing is measured in meter seconds. The area underneath the position time graph has no meaning. Okay? There's nothing. There's nothing. Okay? It doesn't matter. Now, what about a velocity time graph? Does that area have meaning? Yes, because that's meters per second times seconds. Then you get meters, which is displacement. Now, in this particular situation, even though we haven't talked about this a lot, but what would your acceleration time graph look like?
Horizontal line.
Yeah, that would just be a horizontal line at 4 meters per second squared. Okay? Because that's just remaining the constant value.
Does this one give you anything?
Nothing. This is a unique one-trick pony. It's just acceleration. Like slope doesn't really mean anything. This is just kind of okay. All right. Now let's talk about the last equation that's on your sheet, and it has this full-blown vx squared equals v naught x squared plus 2ax times x minus x naught. Okay, and this looks like a horrible equation. It's like, oh my God, this is hell. Okay? This looks much worse than what it actually is. Now, I want to do a little bit of comparison. If you look at the equations that you have v equals v naught plus at. You have d equals 1/2 v plus v naught time. And then you have x equals 1/2 at squared plus v naught time. What's missing, and this is the only one that has a name. This is the one we call that equation, okay? Because Nettie Kumju from Nepal, who sat back there on the back row at one point said, Mr. Burkamp, let's call that equation. And I said, cool, Nettie, let's call it that equation. It's been called that equation ever since. So, what's missing from that equation that's in every other equation? Time. So if you ever have a problem that does not involve time, and you will, okay, go to that equation. Now, for now, accept the origins of this equation. All the other ones I proved where they came from. This is actually based upon kinetic and potential energies, which we will talk about like late November or around December, okay? then you'll see, oh, that's where that comes from. Basically, it's the sum of your two types of energy. Potential energy, which is stored energy, and kinetic energy is the energy of motion, okay? Eventually, you'll see where that comes from and go, oh yeah, that makes sense. So remember this later on in the year when I show you where this came from. So, the short version of this, how it's usually written, and again, don't worry about that x minus x naught unless the squirrel was being launched off of a cliff. You can just assume that the initial position is 0, okay? So unless it's something weird, just assume the initial position is 0. So the short version of this is just go v squared equals v naught squared plus 2x, okay? That's the practical version of this equation, okay? 99% of the time, that's how you're going to use this equation. So here's how this would play out. A car is moving at 4 meters per second and accelerates to, I don't know, 12 meters per second over 16 meters. Find the acceleration. Okay? So this is so here's the anomaly about acceleration. Is that we spend a lot of time talking about acceleration. It's a very, very important concept. But measuring acceleration directly is difficult to do. Okay? Distance is easy. How far did it go? Time is easy. Start, stop. Easy. Okay? Velocity is somewhat easy because all you have to do is look at the speedometer in your car. Okay? So velocities are easy, distances, times, that's simple. Positions are pretty simple. Okay? Accelerations are tough because of the fact that you're talking about this velocity changing over the period of time. Okay? So you have to know what it is and then how the rate of change, and it's just ugly. So this is why a lot of times we calculate acceleration based upon data. So here's the story. So first off, start with this. Even though you don't have to, what would the velocity time graph look like for this? Shannon, what would the velocity time graph look like? Where would it start?
Cars moving 4.
Okay, so we're going to start at 4 meters per second. Then it's going to go up to 12, right? Now, this is important. What sign is the acceleration going to have when you get done?
Positive.
Positive. There's two reasons. Number one, you have positive velocity and you're speeding up. Number two, your velocity time graph is going to have a positive sloping line. So if you do this and you get a negative acceleration, you have done something horribly wrong. Okay? You have done something horribly wrong. How does the 16 meters fit into that velocity time graph?
Displacement.
Yeah, which would be the, so that 16 meters represents the area underneath that line. Okay? Not relevant, but it's just handy information to know. So now, if you set up your V naught tax chart, and again, you do not have to do this, okay? If you're reading through the problem, you're cruising, you got these, don't worry about it. But if you get to a problem, you go, man, I don't know what to do. Set up this chart. So, Isaac Bruce, what's my initial velocity?
4,
What's my final velocity?
12,
Do I have to worry about time? Not part of the story. What about my acceleration?
12.
Nope.
No. 4.
Nope. Let me give you a hint.
We don't know.
You don't know it.
Yeah.
That's what I'm trying to find.
Yeah.
Okay? The 16 meters is my Displacement, that's how far I went, okay? So this is the classic situation where you do not have time. So what are you gonna use?
That equation.
That equation. Now, when I do these problems, you look at my answer keys. I go through the same process every time. I figure out what information I have, I write down the equation, then I solve the equation, and then I find the answer, okay? As complex as these problems are going to be, you have to change this mindset to go, oh, I got an answer. I'll focus on getting the answer. If your sole focus is getting an answer, this is going to be a train wreck, okay? I'm gonna tell you this straight up. You have to focus on the process. So, let's start with this. I need that equation solve for A. So, Francesca, how can I get A by itself?
Subtract V naught squared.
Okay, so I got V squared minus V naught squared,
Divide by 2 and then multiply by x.
divided by 2x. Boom, there's my acceleration. Okay? Now, then I can put in my numbers. Okay, you all want to jump to the numbers thing. Okay? Bad. It's not gonna end well. So, I got V squared. This is why you also have to differentiate between V squared and V naught squared. Okay? Because depending upon if you switch those around, you're either going to get a positive or negative acceleration depending upon how you set this up. Okay, final velocity, that's going to get, what do you say? 12 meters per second squared. So somebody do the math. Take 12 meters per second squared minus 4 meters per second squared divided by 2 times 16 meters. 144 minus 16. Not a huge acceleration. What'd you get? Now, word of advice. When you're dividing by 2 times 16, don't type in divide by 2 times 16. If you do, your calculator will divide by 2 and then take that product and then multiply it by 16. Okay? If you're going to do this, you have to put this in brackets, okay? Because you need to divide by the product of 2 times 16. Not divide by 2 and then multiply by 16. Completely different answers. So, what'd you get? What?
4.
Exactly? Oh, wish I had planned that out. 4 meters per second squared. Now, how would that relate back to Shannon's velocity time graph?
The slope.
Yeah, now you have the slope of the line. Okay? Cool. Got it. Good. Right. Now, I can sit here and work equations, problems all day, right? Until you actually begin to work these problems, it doesn't make any sense. Like, you have to begin to work these problems. So, let me hand this out. And I have much explaining to do before I turn you loose on the assignment. You're welcome.
Can't believe I'm gonna leave this problem until-
Oh, we'll wait until you get into it. You're welcome.
Oh, yeah.
All right, we need paper.
All right, so let me explain a couple of things. Nothing personal. Okay, so on the back side of here, I show you the format in which I want this done. You have to view this from my perspective. Tomorrow night, I'm gonna have 31 assignments to grade. And these are complex assignments to grade. I do not want to deal with 31 different formats of how you think you should arrange your paper. Oh, so horizontally or vertically, or maybe I'll just, box in my answer, okay? I do not have time to sort through 31 formats and try and figure out how you chose to do these assignments, okay? So, for those of you that have had me for AP Chemistry, you all know the drill already, okay? Ron, just smile. So, here's your sheet of paper. First thing you're gonna do is you're gonna come over about 1.5 inches, something like that, and you're gonna draw a line down that paper. What goes in this left column is the answers. That's it. Okay? The answers go there. Over here goes the work that generates that answer. When I give you assignments like this, nothing, you can write on this, but nothing gets answered on the sheet. You can circle the multiple choice, whatever. I am not grading anything that's on this piece of paper. The only thing I'm grading is what's on that notebook paper, okay, or graph paper, depending on what you want to do. So, yes, the first questions are multiple choice, but you put the answers not on here, on that sheet of paper. So, you're going to come in here and you go, okay, 1, 2, 3, 4, 5, 6. None of those multiple choice questions, trust me, none of them require any calculations. So you can just go 1, 2, 3, 4, 5, 6, answer the question, okay? Don't stack them horizontally. You don't get bonus points for doing this in the smallest amount of space, okay? I'm just gonna become irate as soon as I see your paper, which is a bad way for me to grade, okay? Now, when you get to number 7, I say, can an object move with uniform acceleration and constant velocity at the same time? I then explained, I said, note, 0 meters per second is not an acceleration. That's like saying, I have no money in my bank account, but yet I still have money. No, you don't. You're broke, okay? So 0 meters per second squared does not count as an acceleration. Now, when you answer number 7, you can write that explanation and carry it across both parts of it. The heart and soul of this is when you get to a question like number 8, okay? So I'm going to show you exactly what I would do if you gave me number 8, okay? We're going to work number 8 together, so exactly what I want. So number 8, you got a Corvette starts at rest, undergoes uniform acceleration for 4 seconds. If the car's displacement during this time interval is 50.4 meters, what is the value of the acceleration? So let's say you read that problem and you go, oh my God, what kind of psycho problem is this? If you can't figure out what information that you have and what information that you're trying to find, you are just dead in the water right from the beginning, okay? So, I would recommend, until you get comfortable with this, do the V naught tax statement. What's your initial velocity? 0. Why?
At rest.
You're told that the Corvette is at rest. Oh, okay. That makes this easy. My initial velocity is 0. What else do you have?
Distance.
I got a distance of
50.
50.4 meters. What else you got?
Time.
You got a time of
4 seconds.
4 seconds. And what am I searching for?
Acceleration.
Acceleration. So realistically, this is a simple way to calculate acceleration. You start the car, it's at rest. You lay out 50.4 meters, you take your stopwatch, go, boom. Stop it when it crosses 50.4, okay? Those are easy things to measure. Are you going to worry about the final velocity of the Corvette?
No.
No, it's not part of the story, okay? So, don't worry about the final velocity, because I don't ask you to find it, okay? It's not part of the story. So at this point, and here's the beauty of this test on Friday, this is going to be the test with the smallest number of equations possible that you can use. Okay, literally, this is going to be the test with the smallest number of possible equations. You only have 3. Technically, there's that fourth one, d equals 1/2 v plus v naught times time. You only have 4 equations to choose from. Okay, that's it. There's only 4, if you count the other one. So, now that you know what's happening, so you need to find an equation that relates distance, acceleration, time, and initial velocity. What do you got? The second one. Okay?
X equals 1/2 AT squared.
X equals 1/2 AT squared plus
V naught.
v naught time. Okay? Cool. I'm telling you, this is exactly what I would do if I were working this problem. Now, here's the other thing. When I go to grade your paper, I want to give you points. But I will only give you points if I can track what you have done. If all you've done is randomly write down numbers, no equation, no units, you have randomly jotted down numbers. No thought process, no organization whatsoever. And your answer is wrong. I care for you all deeply, but I am not going to waste a second of my life trying to sort through random numbers. Not going to do it. Now, personally, I always take it as a challenge. If a kid gets an answer wrong, I want to go through and figure out what you did wrong. Hey, did you have the wrong equation? Did you have the right numbers? Maybe you just punched numbers wrong into the calculator. Okay? So I want to try and figure out what you did wrong. But I can only figure out what you did wrong is if I see what you did in some type of logical manner. So here's what I want to do. I don't have to worry about the V naught part of this because the vet started at rest. Okay? So I don't have to worry about that part of it. Okay? So I need this equation solved for acceleration. So what am I going to do? I hate the fractions. So what am I going to do first? Multiply by, divide by, and that's going to get you acceleration. Cool. Now I know what I'm doing. Okay? I've conveyed, here's the equation, and now I've solved it. Now I can put in the numbers. You have to avoid the temptation to go, I just want to go to put in numbers. Okay? No. No one is going to pay you $80,000 a year to randomly write down numbers. Okay? They're not going to. They're going to pay you $80,000 because you know what the numbers mean, and you can manipulate them. That's what they're going to pay you $80,000 to do. Now I can come here and go, okay, I got 2 times 50.4 meters divided by time, which is going to be 4 seconds. That's going to get squared. So first off, do my units work out?
Yes.
Yeah, because I get meters per second squared. If the units don't work out, guess what? Doesn't matter. It won't work. Here's what you're going to forget to do. You're going to forget to square the time. You're going to write it down, and then you're going to get so excited, like, oh, physics. And then you're going to forget to square the time. And don't say that Mr. Burkamp, don't be silly. We won't do that. Yes, you will. Okay? I'm psychic. I know what you're going to do. So, what do you get as an answer?
6.3.
What'd you get? 6.3 exactly?
Yeah.
Okay. So you need to write that as 6.3, because all my data has 3 significant digits. So that's going to be 6.30 meters per second squared. I can see the equation, I can see the solved equation, I can see the numbers with the units. Okay? Now, here's the most critical juncture. When you get to number 9, okay, you need to leave a space in between 8 and 9, some people go crazy. They like draw stars and planets and they shade it. You don't have to do that. But at least leave a visual space, because here's how you need to view this. Imagine it's your paper. Is the last one I'm going to grade. It's 11 o'clock at night. I'm cranky. Okay? I'm cranky. And all I see is a jumbled mess. You didn't follow the format. I can't read it. There's no units. How happy am I going to be? Not. Okay? And at this point, I will write, I'm already annoyed on your paper. Okay? So, keep me happy. Okay? View your assignment through these eyes, not through your eyes. Okay? And imagine these eyes at 11 o'clock at night. And again, I'm not doing this to be an ogre. Okay? I'm not. I'm doing this because it forces you to stay organized and it makes it easy for me to grade. Okay? So when you get to number 9, do not put the answer to number 9 below the answer to number 8 and then have the work for number 9 here and then draw an arrow going, see work. I will flip out. Okay? I do not do arrows. Don't. Bad. You put the answer to number 9 right here. And if you're not sure how I want this done, look. Okay? This is why I gave you this example of how I want this done. If you're not sure, maybe I should look at the example. And if you're not sure, ask Ryan or Cooper, because they got yelled at last year for not following the format when they were in my AP chemistry class. Okay? All right? Okay. So, when you get to number 9, notice that number 9 has a whole bunch of different parts. A, B, C, D, E. Okay? Do not stack the answers for number 9, A, B, C, D up here, and then put the work down somewhere else. You keep those answers right beside. Now, on number 9, you want to make a velocity time graph. You can draw your velocity time graph on this assignment. You do not have to do that on another sheet of paper. If you really want to, you can. Okay? But if you just want to come over here and go, here's the velocity time graph, boom, that's cool. Okay? But